Okay. Good morning, good afternoon once again. Good afternoon once again. The time is 1:25, so we can start. So today we'll be looking at digital electronic introduction to digital electronics. We're looking at the representation of digital electronics. We have the analog and then digital representation. Then we'll delve into digital systems and analog systems, right? Then we'll look at logic family, right? Look at the logic family. Then we'll delve into computers, the types of computers. Then we'll look at the central processing unit, the what makes up the central processing unit. So we'll look at them. So when we say digital electronics, so first you have to know what electronics is, right? You have to know what electronics is. So basically, so can someone hear me? Hear me, sorry. Am I clear enough?
Yes.
Okay. So when we say digital electronics, you have to, like I said, you have to know what electronics is and then what digital is, and then we'll combine them together to get the definition. So basically, electronics is just what the study and then behavior of what electrons, sorry. So it's the study of the behavior of what electrons. So how electrons affect um, uh, conduction, right? So we know that when you talk about conduction, then the conversion is done by what the electrons. So the movement of electrons, we know the movement of charges, what is what current. So when electrons move, it produces what current. So electronics basically is the behavior or the study of the behavior of what electrons. And digital, when we say digital means just what we know, zeros and ones, right? So zeros and ones, so representing something in a digital form. So when you say digital form, it means that form is what discrete. When you say discrete, it occurs at what a constant what interval. So that's what discrete means, and that's what digital and then electronics mean. So when we combine digital and electronics, basically digital electronics is just what a circuit, right? That is just a circuit that involves what? The manipulation of a system in a digital what? Form, right? So it's just a system or a circuit that what involves the manipulation of a system in a what a digital what form. That's what digital electronics. So we look at, like I said last week, we looked at assessment, how your assessment is going to be done. So exam score is 60 marks. Your midterm assessment is what 20, and then the remaining ones take what the 10. So assessment and all takes what the 10. So like what I said, digital electronic involves circuit that operates using what digital signal. So we see as digital signal. Digital signal is one signal that is what discrete that is discrete in what time and then discrete in amplitude, right? So we say it is. Hold on, someone sent me a test. Okay. Hold on. Right. So basically, digital electronics involved for circuits that operate using digital signal. So a digital signal is a signal that has discrete signal, a discrete time interval, and then what? Discrete amplitude. So when you say discrete, we say what? Discrete means it's what? It's a constant what? Has a constant interval, right? It's constant interval. So we'll look going for a look at what the representation of digital signals and then representation of what analog signal. So coming. So uh and basically digital electronics forms or digital circuit forms what the backbone of any what of our modern communication systems, right? So even currently, our computers, our calculators, our modems, and all this design more in terms of what more digital form. They are in digital form. So we all know that there are two types of information, right? We have the analog information, and then we have what the character information. So when I say analog, a signal that is continuous in nature. So let's say let's write something. So I want to show you something here. Are you seeing what I'm drawing? Can someone see me? What I'm drawing? Can someone see what I'm drawing?
Yes,
So,
sir.
so this is an analog signal. What analog signal means is what it means is that's what a continuous amplitude and then continuous what time, right? So you can have here to 1.5. You can have this part to be 1.5. You can have this part to be what 2.5. You can have this part to be um 3. I mean, it's not at a constant what interval, but for a discrete digital signal, it is what constant interval, right? So all the systems we have here now, our modern system are what in digital form. So we have information that are analog and then what character. Character. When I say character, it basically means like you want to send on a test. What's in WhatsApp? Want to send a text message, you say, "How are you?" How are you is the what? The character, right? How the H is just a character, right? Or it's an alphabet. So how are you is a type of what? Information. So that information, so we call it what? A character what information. And then this form of information is what? Is what we call the analog what? Information. So before our computers or our calculators can display whatever we have sent, you have to convert it to what? Zeros and ones. So that zeros and ones is what we call what the digital signal, right? There's zeros and ones, what's called the digital signal, right? And then that digital signal, before it can be um sent over to the receiver or to the computer, it must be what converted to a waveform. It must be converted to a waveform. So you can have something like this. So this is what we call what a digital what signal. So this is what we call a digital signal what waveform. So this after encoding this or after um yes, encoding this, changing this into zeros and ones or binary, you will get this type of what waveform, and then we send this info waveform to the channel. So that's what happens in most digital systems, right? So they are the backbones of our modern communication systems, right? And then, like I said, there are examples of the examples of digital system. We have the computers, right? And then the computers are made up of central processing unit and memory and then the storage, right? So the CPU or the central processor, just the brain of what the computer is that system that performs what arithmetic operations and logical operations. And then I say at the same time do what you call control. So when you say control, it takes the control means it takes the information from what? A memory. So the memory basically is the area where we store the information the same way with the storage as well. Then we have another form of digital electronics. Digital systems is what mobile phones, right? So the mobile phones are made up of the same processors, memory, and the others. And then you have home appliances like the microwave, washing machines, smart home devices. They are all what digital systems. And then automotive system like you have the engine control unit and the safety features. All these things are digital systems, and you have the medical devices as well, which are made up of what the imaging equipment, patients, and diagnosis. So, like I said, before you know what a electronics is, you have to know what electronics is. So it's basically the electronics is basically a branch of what physics and technology concerned with the behavior and movement of what electrons. So it's just a study of the behavior and movement of what electrons. So we can also say that electronics is the branch of science and engineering that deals with current or conduction. And I said movement of charges gives what a current, and then the charge is more of what electron, right? So current conduction phenomenon and in the vacuum or a gas, right? So these are all what definition of what electrons. So like I said, we have two forms of numerical representation of what digital representation and then what digital what representation. So we will first look at the digital representation. So digital representation or the digital system. So you can say digital representation is just what the digital system. So it's concerned with what the manipulation of logical information of physical quantities are represented in what digital form. So these are that are represented in digital forms. When you see digital forms are what there's the zeros. Digital forms are the zeros and ones, right? So digital forms are the zeros and ones. So basically, what it means is that it can take only what values. So when I say discrete values, like I said, it's constant what interval values, right? So you can so when I say constant interval forms, you can go 1, 2, 3, and continuous like that, right? Then 4. The interval between the first and the subsequent one is what? 1. Then it follows, and then the interval between the subsequent one and then the next one is what? Another one. So the quantities can take what? Only what? A discrete for value. So if the interval between them is not equal, then we say it's an analog signal. So we have 1, then we have, let's say, 1.5. 1.5 here. Then we have then we can have, let's say, the next value can be 3. Right. So it's not at a what discrete interval. So this type of signal is what we call what analog signal, right? This type of signal is what we call analog signal. So this is basically what these digital systems are, right? So they manipulate information or physical quantity that are represented in what in digital form, like what you see here. So and then we look at the analog representation. So the analog representation is just going to be the opposite of what digital representation. So analog representation is just the combination of devices that's designed to manipulate logical information or physical quantity that are represented in what analog form, right? That are represented in analog form. So that is what analog representation. And we know what you should know is most of our real world events are what analog signals, right? So like something like um, earthquake, floods, all these things are what analog signals. And then we before we can get the actual intensity of that signal, then we have to convert that signal because you are going to do what you call what calculations. So that calculation is going to be done by the computer. So before we can do that calculation, we have to convert the analog signal to what a digital signal. So it's to a form that so the digital signal is just a form that the computer would understand, right? So you have to go through multiple intensive calculations before you get the output at the what as the display on the computer. So this is one disadvantage of what digital signal over what analog signal. So like I said, I've explained analog systems already. So a quantity that is represented by a voltage, current, or meter movement that is proportional to what the value of that quantity. So the characteristics is what they they can vary over continuous range of what values. So they are continuous in time. So they are continuous in time. I have described what this digital representation is already. So an example is just what the digital watches. So then the characteristics is what value changes in discrete what terms, discrete what steps. So these are the major differences. We see analog is equal to what continuous and digital is what discrete. So step by step. So this is the waveform. This is what I've done. This is the waveform of what the analog and then digital signal. This is the waveform of the analog and digital signal. So this point, this point you are seeing here is what you call what the peak. It's what you call the peak value of what the amplitude. We call it the peak value or the what amplitude. So the amplitude is just the peak value the signal what reaches, right? So this is the amplitude, this is the amplitude. In other words, we call this the trough, call this trough, call this trough, call this trough, and then we call this crest, right? Call this crest. So they are just what the amplitude or the peak value, right? The peak value, right? So the interval, the time interval between this part and then this part is what we call the sample or times. So this is over the time, this for the amplitude. So this is the representation of analog signal, and then this representation of what digital signal. Digital what signal? This is the representation of digital signal. So this is just the word the waveform of for digital signal. This is the waveform of digital. So today we are looking at what digital signal and then what analog signal, right? So this is just a question for you. So from whatever we have discussed, which of the following involve analog communication and which involve digital what? Sorry, which of the following involve analog quantities and which involve digital quantities, right? So, like I said, this question will be for you. The current flowing out of an electrical outlet. So, the first part is it analog or digital? From whatever we have explained, a question to you guys. Please, the first one is it analog or digital? Current flowing out of an electrical outlet. So, like I said, analog information, examples of analog informations are our real world informations, our real world occurrences, they are analog. Almost everything in our world is analog. Then we have the voltage flowing through a battery is analog signal. We have a current flowing through an electrical outlet, which is not what analog what signal or analog quantity, right? Then we have it driving here. Let me show you. The meter movement are what analog what signal. So the first one, the current flowing through analog current flowing out of an electrical outlet. The first one is an what analog what signal. The first one is one analog quantity or analog what signal. Analog signal. And then the temperature of a room. What do you think the temperature of a room? Is it analog or digital? Analog or digital? Is someone here?
Analog.
Temperature of a room. Okay. Because we can have thank you very much. It's analog signal because you can have constant interval, you can have what's the name 16.5, 14.5 and all that. So it's analog signal. And then the third one, the sun grains on the beach. The sun grains on the beach, which is it analog or digital? The sun grains on the beach, analog or digital? Analog quantity or digital quantity? Sun grains on the beach.
No, digital.
It's a digital quantity because you can take a single grain on the beach, right? You can't take half. You can take a single grain at the same time. You can take twice, right? So it's a digital quantity. Then automobile speedometer, is it analog quantity or digital quantity? So let me leave the two for you. Find out whether automobile speedometer is what. So here we are looking at the reading, right? We are looking at the reading of what the speedometer. Then we look at the 10 position switch. So these are for you. Yeah, look at it. So I've talked about the digital systems already. These are just repetition in the slide, the same way the analog systems, they are just repetition, right? So, I mean, so what can you say? What are the disadvantages? You need to look at the disadvantages and then advantage of what? Digital signals over analog signal. So, from whatever you have said, can someone give me one advantage of what? Digital what? Signal, quantity over analog quantity? Or the advantage of digital systems over analog what? Systems? Only one. Advantages of digital systems over analog systems. Why do you think our systems are now going to the digital mode instead of what the analog what mode? So only one digital systems, advantages of digital systems over analog systems, only one. Hello, someone here. So only one. Advantages of digital systems over analog systems, only one. Only one. Only one advantage.
The
And then
data storage and
Mhm.
retrieval.
Data storage and retrieval. So we say, like I said, so digital systems. So first, they are easier to use and what reliable. They are very reliable, right? When I say reliable, I mean you can so when they are reliable, it can't fail you at any time. Unlike the analog systems, right? Analog system can fail at any time, but for digital systems, before it will fail you, it will give you a warning signal that it will warning shot that oh, my system is actually what calming down or is actually failing. So what beware. So they are reliable and then they are easier to use, right? And then they are also cheap. They are cheaper, they are less expensive as compared to what analog system, sorry. They are less expensive as compared to what analog what systems, right? So I mean you can take a small, let's say something like an integrated circuit, IC. So IC is just a small substance that performs a PCB, right? Printed circuit board on a small printed circuit board, and then you get your digital systems. But unlike analog systems where you have to get a bulky system before it will function, something like our cathode ray tube. Before you get a signal, what chin chin, and then before what you get this one. So they are less expensive as compared to analog system, sorry. And then like you said, the systems are easier to design first. Information storage is easy. So the information storage is easy. Then accuracy and precision are great. So the tendency with you to get an accurate information is much higher in digital systems. And then operation can be what programmed, right? So operation can be programmed. And then the digital system are less affected by what? Are less affected by noise, right? They are less affected by noise, unlike the analog systems where any small any small forms of noise can distort the signal or it can affect the signal. But in digital systems, it takes what a much or a greater noise to affect the system. Even with that, the digital system is still easier to what to regenerate the signal. So if the digital signal is distorted by a noise, you can easily generate the original signal by just what amplification. But in analog systems, when the signal is distorted by the noise, it passes through, it takes a lot of effort to what get the signal back. So this is also another advantage of what digital system over what analog system. So we have exhausted the digital system. Can someone give me one disadvantage of what digital systems over what analog system? One disadvantage. I mean, in this world, there is always going to be advantage and what disadvantage. So even though digital systems have much greater advantages over what analog system, but there are still disadvantages with digital systems as compared to what analog systems. So give me one disadvantages of digital systems over what analog systems. One disadvantage. One disadvantage of digital systems over analog systems. One disadvantage. One disadvantage of digital systems over analog system. Only one. Is someone here? Only one disadvantage. Only one. Only one disadvantage. Is someone here? Only one disadvantages of digital systems over analog systems. Only one disadvantage.
They can be more expensive.
Are you sure they are more expensive? I made mention that the digital systems are less expensive than analog system, right? So they can't be. So let's say when you say expensive in terms of production, right? In terms of
Yes, sir.
production, yeah, in terms of
Yes, sir.
production, yeah, in terms of production, it's quite expensive, but you can for a digital system, like let's say the IC, you can put a lot of IC on a small PCB, right? Then it will perform its function. That is what you call it less expensive. That in terms of less expensive. But when it comes to the disadvantage, right? When it comes to the disadvantage, so one one basic disadvantage is that I already explained that in when I was talking about the digital systems and analog system. I said our real world informations, right? Or our real world events are analog systems, right? The analog signals, right? So before then we are using computers and then calculators and all that. So before we can know the intensity of what of such events, you have to convert that event what a digital event, right? And then the conversion takes what a lot of what mathematical or intensive mathematical equations, right? It goes through intensive mathematical processes or equations or calculations before you can get the actual reading on what um on our screens, on the computers, and wherever you are measuring the thing from, right? So one disadvantage of digital systems or analog system is that digital system go through what intensive what processes, right? It goes through intensive processing to get what the output or the display, right? It goes through what intensive processing, or it goes through intensive mathematical processes before we can get the actual information at the receiver, right? That is the one prominent disadvantage of what digital systems over what analog system. And then another one is what synchronization. Synchronization. So in digital systems, the function of one component depends on the function of other components. So all the components must be in sync. So they must work simultaneously to get the output at the receiver, right? So that the component must be in sync. They must work simultaneous, or they must work hand in hand, right? They must work hand in hand to get the display at the receiver, right? They must work hand in hand, unlike the analog systems where each component do not depend on each other. I mean, one can be doing each thing, and then the other will also be doing each thing. So, I mean, I've given you two. So it has to do with synchronization and then what intensive mathematical processing. So you can look for the other ones as well. Like I said, there's only one major drawback when using digital systems, right? The techniques. So our world is what analog. So when dealing with analog input and output, three steps might be what followed. We have to convert our real-world analog input to a digital form, like what I've said, and process. So the process is what we call what? Is what we call, that's what I said. It goes through what? Intensive what? Mathematical processes to convert the digital output to what? The actual what? Intensity of the real-world event we are measuring, right? So this is what I've explained already. So this is what I've explained. So the image you see here are just what the advantages of what digital systems over what analog, or the difference between analog systems and digital systems. So the analog signals represent what physical measurements, and then digital signals are discrete and generated by what digital modulation. And then the waveform is sine. This is what we call what the sine wave. What you see here is what we call what the sine wave. And then this is what we call the square wave. The square wave, right? The square wave. Then the representation, continuous range of values represent what? Information. So they are continuous in nature. And then digital systems uses what? Discrete what values, or constant interval values to represent what? Information. And then data transmission affected by noise during transmission, and then noise immune. They are actually immune to noise, right? Even it's going to be less affected. So response to noise, most likely to get affected. And then for digital system, like less likely to get affected. And then the bandwidth, yes. Then we'll talk about the bandwidth. So in digital system, the bandwidth is small as compared to what the analog what system. And then the memory you have stored in the form of what wave signal. So this is it, or the sine wave, and then store data in the form of binary bits, so zeros and ones. Yes, so zeros and ones. So the computer understands what only binary digits, zeros and ones. So in order to understand this sine wave, this computer has to what convert this sine wave towards zeros and ones, and then it stores it, right? And examples of analog signal can be our human voice, earthquakes, and all these things. They are all what analog signals, analog systems. Then we have for digital systems, we have for the computers, and then the CDs, compact discs, and then digital versatile discs. So this is a summary of whatever we've gone through. Any question on that part? Any question on that part for me? Any question? Can you go ahead, please?
Yes, sir.
Yes, sir.
Okay. Thank you very much. So our next topic will be what? Logic families, right? Logic families. So we see logic family. It is just a group of what? Electronic digital circuits fabricated by the same semiconductors, right? So it's just a group of digital circuits that are fabricated by the same semiconductor technology. So there are different type of semiconductor technology. So I mean, you all know what semiconductor. So in between properties in between conduction and what insulation. So that's a semiconductor. So logic family is a group of electric digital fabricated by the same semiconductor technology to perform what? Logic operations. To perform logic operation. So in the slides, so this is something I've learned and I know. So in the slides, it says what? It refers to a set of what techniques used to implement logic. So when you say logic, this is just what the operations of what operations of a circuit, right? So for a logic, we have what the AND the AND gate, we have the OR gate and the NOR gate. We'll look at them in our subsequent lectures. So logic family represents it refers to a set of techniques used to implement logic within large scale integrated circuits such as central processing or memory, right? So these logic family are basically implemented on what memories and then central processors. So they are done by what the help of what integrated or circuit. So there are different types of what logic family. There are different types of logic family. So there are the type. There are two types, right? There are two categories. Sorry, there are two categories. So the first category is one that was done by what BJ BJT. So BJT we call that. So the first category is BJT. Logic family that was built from what? That was built from BJT. So the BJT means bipolar junction transistor. Bipolar bipolar junction transistor, sorry. Bipolar. What let me ask, what is a transistor? What's the function of a transistor? Transistor. Function of transistor. Function of transistor. Transistor function. Function of transistor. Anyone here?
Yes, sir.
Sir,
Hmm. Who is speaking?
please can you say it increases the strength of weak signals?
Yes, so the increasing of the strength of the weak signal is what we call what? Amplification. Transistors, we first it's just used for what? Amplification of signals, and then it's used for what? Switching. All right. So switching and then what? Of what? Transistors. So I said there are two categories of logic families, right? You have the ones that are built from bipolar junction transistors. Then we have the one that are built by what? Built from MOSFET, right? MOSFET. They are built from MOSFET. They are built from MOSFET. So MOSFET is just metal semiconductor field effect transistor. So the M is metal, O is what? Oxide, S is semiconductor, F is field, and the E is what? Effect, and then T is the what? Transistors. So you have two categories, ones that are built from bipolar junction transistors or MOSFET, right? So we'll look at them one by one. We'll look at the bipolar transistors, the ones that are the types of what logic family that were built by what? They built from that bipolar transistor. And then we look at the one that was built from what? MOSFET, right? So bipolar transit transistors has to do with, when we say something is bipolar, it means what? It has two carrier, it has to do with what? Current, right? So it has two current carrier states, right? We have the positive and then the negative. That's basically what bipolar transistor means. Then we have the MOSFET. The MOSFET deals with this deals with what? Voltage, what? It deals with voltage. So MOSFET deals with voltage. So it's just a voltage controlled what? Transistor. Where the bipolar deal is a what? Current controlled what? Transistors. So we look at them. And before a circuit can be grouped in the same family, it must share what? Compatible voltage levels. It must share compatible voltage levels, logic states, and then power supply characteristics. So each logic family has its operating voltage level, each logic state, and then power supply characteristics. So without that, you can't group them in the same family. So like I said, we look at the ones that are built from the BJT, with the bipolar junction transistors, then the ones that are built from MOSFET, right? I said MOSFET deals with voltages, so it's a voltage controlled transistors. And then we have the bipolar, which deals with current controlled transistors. So for the BJT, we have this type. So these are built from BJT. These four, 1, 2, 3, 4. These four logic family are built from what? They were built from BJT. And then this was built from MOSFET. These were built from MOSFET. They were built for MOSFET. So under the BJT, we have the emitter coupled logic. You have the emitter coupled logic, which are just transistor families, or they are just logic families that prevent transistors from what? Entry into the saturation region. When you say saturation region, it's just where a region where the transistor has exceeded its operating limit, right? It has exceeded its operating limit. So the emitter coupled logic family is just a family that prevents transistors from what? Entering the saturation region. Then they are just like I said, they are made from what? Bipolar junction transistors. They are very high. They have a very high speed, right? They have a very high speed. Then they can change state at a very high speed as well. So one, it prevents the transistors from entering into saturation region. It has a high speed. Then you can change state at a very high speed. Then we have the resistor transistor logic. So the resistor transistor logic and then the diode transistor logic are obsolete, right? They are older. They are not in use again, right? They are not in use again. So the resistor transistor logic and the diode transistor logic are obsolete. They are not in use again. So for the resistor transistor logic, like I said, they are obsolete. They are built using resistors as the input, right? So you have the input network and then what? The switching network. So for the resistor transistor logic, we have the input network and then there is the switching networks, right? So the input networks is done by what? The resistor, and then the switching network is done by what? The transistor, which is what the bipolar transistor. So they are built from the bipolar transistors. So it's again, it involves minimal number of transistors, right? So it involves minimal number of transistors. Then we'll come towards the diode transistor logic. So the diode transistor logic is also what obsolete, like I said, or they are older. So it is also built from what BJT. It's also built from BJT diodes and then resistors, right? So the here the logic operation or the logic gate function is performed by the what diode. So the diode transistor logic operation family, it is the diode that performs for the logic function, and then the transistor performs what the switching what function or the amplification what function. So that's what the diode transistor logic. But in transistor to transistor logic, here in this family, the logic operation and then the switching operation or the amplification operation is done by what transistors, right? It is done by only what transistors. It is done by only transistors, and then they are made from what BJT as well. They are made from BJT. They are made from BJT, and then they consume more power than what the CMOS, right? We will look at it. So they consume more power than CMOS, but they consume less power than the remaining what the first three logic families. So the transistor logic consumes more power than the CMOS, the complementary metal oxide semiconductor logic, and then it consumes less power than what the three families, right? Consume power than the three families. So, like I said, the logic and then amplification is done by what transistors, right? It's done by transistors, and then the diode transistor logic. The logic operation is done by what diode. Then the switching on amplification is done by what transistor. And then the resistor transistor logic the same way. Logic operation is done by what the resistor, and then the transistor is the one that performs for the switching on the amplification. And then for the emitter coupled logic, the emitter coupled is just to prevent transistor from entering into what the saturation what region. Then we'll come to what the CMOS. Like I said, the CMOS are built from what? Are built from MOSFET, right? They are built from MOSFET. So CMOS deal with what? Voltage control transistors. So it deals with what? Voltage control transistors. So the complementary metal oxide are built from MOSFET, and then it deals with what voltage control transistors, which are used to what amplify or switch electrical what signals, right? They are used to switch after. I mean, it's a voltage control transistor which is used to switch, then used to switch to amplify electrical what signal. So there are some characteristics of what the CMOS over the what the three or the four logic families, right? So for the CMOS is currently is the most used logic family now, right? It's the most used logic family now. I said the resistor transistor and then the diode transistor families are obsolete. They are not in use again. We still use the TTLs and what the emitter coupled logic, but the CMOS is what the most commonly used word logic family now. It is mostly used in microprocessors, microcontrollers, RAMs, and even other what logic circuits. So it has low power consumption, right? It has low power consumption as compared to what the four logic family. It has low power conversion. And then it has what a high noise immunity, right? It has a high noise immunity. It has a high noise immunity. Then before you can choose any logic family to use, before you can choose any logic family to use, there are some parameters what you have to look at. there are some parameters you have to look at. We have the speed. So if you want a higher speed, you go with what the CMOS, right? So the speed basically is just the rate at which logic family operates. The logic family operates. So before you go for what's the name? Any logic family, you have to get um all the charts. I mean, the charts are there, which talks about the speed, the power dissipation, packet density, fan in, fan out, noise immunity, or margin availability and operation. So the speed deals with what the rate at which the logic family operates, and the power dissipation is just the amount of power, right? It's just the amount of power the logic gate consumes while operating, right? It's just the amount of power the logic gate consumes while operating, or the logic, yes, the logic gate consume while operating. We have the fan in and fan out. So the fan in basically is just the maximum number of digital inputs, right? It's just the maximum number of digital inputs a signal logic can accept, right? It's just the maximum number of digital inputs. So it's just the maximum number of inputs that the digital can accept. So let's say you have a logic gate like an AND gate. An AND gate basically has, or it accepts at least two inputs, right? So when what the fan-in is, what you call the fan is just the input. So for the fan-in for an AND gate is for two, or at least two, right? So the fan is just the number of digital input a signal as a single logic gate can accept, and then the fan out is the maximum number of identical inputs, right? It's the maximum number of identical input a signal, is the maximum number of identical input a single gate can drive without causing a drop in what performance. So the fan out basically deals with the output, or it's just with the output that a logic give without what drop in performance. So you find out is the maximum number of identical inputs a single gate can drive without causing a drop in performance. What finding and find out. So the noise immunity or margin. So the noise immunity is just amount of noise or a circuit can tolerate, right? So the noise immunity or margin is the amount of noise a circuit can tolerate. So it's just the amount of noise a circuit can tolerate. Then we have availability. So the family you are choosing, is it available on market? Is it easy? Answer, if you're able to answer these questions before even trying to trying to go in for that family. Then the operating frequency. So you just have to know the for your work, which operating frequency are you going to do. So if you know that operating frequency, then you know what the family have to choose, right? So the operating family. So I mean, like I said, the logic families, they all have their speed limitation, the speed limit, power limit, parking density limit, fan in and fan out limit, noise immunity limit, availability as well, and then the operating limit. So if you are working and then you're operating your work or your project, you're operating in let's say 3 gigahertz, right? You can't go for the obsolete ones, or the resistor transistor logic, or the diode transistor logic. You can't go for it, or even the transistor logic. You can't go for it. You can go for what? The CMOS, right? You can go for the CMOS. So all of them have their what? Frequency limit, noise immunity limit, fan in and fan out limit, packet density limit, power dissipation limit, and then the speed limit. So I've explained what the emitter coupled logic, or I've explained everything about it. So the emitter coupled logic is a logic family with the current, like I said, BJT deals with what current. So in which current is steered through bipolar transistors, right? To implement logic function, the characteristic is what? It prevents what transistor from entering into what? the saturation region and can change state at a very high speed. That's what I said already. Then resistor transistor logic, I've explained that one as well. I said they are obsolete. So it's a class of digital circuits built using resistors as the input network. Like I said, so we use the input and we use the resistors, and then for the switching and then the amplification, we use the bipolar junction transistors, right? So the primary advantage of what the resistor to transistor logic technology is that it involves what? It involves a minimal number of transistors, like I said. And then the obvious disadvantage is that it's a high current dissipation when the transistor conducts, right? So it displays a high current when the transistor conducts, right? Or when the transistor performs its function. So it displays a high current, right? Then we look at the diode transistor logic as well, which I said is also obsolete. So it's a class of digital circuit built from bipolar junction transistors, like I said, diode and resistors. So it is called DTL because the logic gating function is performed by a diode networks, and then amplification function is performed by a transistor, like what I said. So the DTL has a major advantage of increase funding. So it has an increase with higher fan in. So like I said the fan in is just the maximum number of input a single gate can take or can accept. So you have increase fan in. Then you have the transistor to transistor logic, which is also built from bipolar junction transistors. So it's a class of digital circuit built from bipolar junction transistors and resistors. So it is called a TTL because both the logic gating function and the amplification function are performed by transistors, right? So the logic function and then the amplification function, the switching function is performed by the transistors. And then the one advantage of TTLs is, or disadvantage of TTLs is it consumes more power than the CMOS, right? Like what I said. And then when compared to the other logic family, the ECLs and then the others, it uses less power and it has easier design rules, but it's typically slower. So these are this is the disadvantage and this is the advantage and this is the disadvantage. Then we look at the CMOS, right? The complementary metal oxide semiconductor logic. I said it's built from MOSFET, and then it is used in mostly microprocessors, microcontrollers, static RAMs, and other digital logic circuits. And I said it's the most commonest used logic family available. And then we have some essential characteristics which are high immunity and low power consumptions, right? I've explained this one already. It's just a repetition. Then we'll come to the computer systems, right? Come to computer systems. So computer systems. We look at the computer system is just It's just the makeup of a computer. It's just the makeup of a computer. So look at what a computer is. Then we look at the makeup of a computer. Then we look at some types of computers. We have the mainframe and the others. So basically a computer is a system, right? It's a system of hardware that performs arithmetic operations, right? Then manipulate data and makes decisions, right? So the data is usually in binary form or digital form. So that is a computer. You and I know that computers are faster and more accurate than human beings, right? So they do work at a faster rate as compared to human beings. So before a computer can perform a function, you need to give it instructions, right? You need to give it instructions. So after you need to give it instruction, a complete instruction. So let's say how are you? How are you is an instruction, right? So how are you is an instruction, then the computer will perform that function, and then you will see it as your display. So before a computer can perform a function or operation, you need to give it a complete set of instructions. And then that complete set of instructions is what we call a program. So this set of instructions is called a program, and the program or the instructions which represented in the binary form are stored in the memory unit, right? Or they are placed in the memory unit. They are placed in the memory unit, and then there are major types of major types of computers, major parts of computers. We have the central processing. We have the central processing unit. We have the storage unit. We have the input unit. We have the output unit. Right. We have the storage unit, the unit. We have the central processing unit, like I said. So the central processing unit is just the brain of the computer. So it is the one that helps to perform the logical operations and then the control functions, right? So each major part can be broken down into some functional units. So you have the input unit, you have the storage unit, you have the output unit, and you have the processing unit. So the processing unit is what we call the CPU. So all you need together, all you need function together to carry out the instruction given in the program, right? So all unit performs, or they come together to perform the function given in the program. So this is the basic diagram of what a digital computer. So you have the data or the information source, data and the information source. Then, so like I said, the information can be in terms of what textual message. Then it can be in terms of analog information. Then you come to the input. So your input, example of your input can be your keyboard, your scanners, and everything. Right. So they help you to input or they insert the instructions into the computer. Then you come to the central processing unit, which is the processing unit itself. So the central processing, you have the arithmetic logic unit, you have the control unit. Right. You have the arithmetic unit and then arithmetic logic unit and then the control unit. So the arithmetic logic unit helps you to perform mathematical calculations, right? It's the one that helps you to perform the mathematical calculations, or it helps you to perform and then decode whatever message that was sent to the central processing unit. And then control unit, the control unit uh, is the one that fetches. You could see the arrow here. Is the one that fetches the instruction from the memory, right? It fetches the instruction from the memory and then decodes what they mean before sending it to the arithmetic logic unit. So the control unit is the one that fetches the information from the memory, then decodes the signal or the information or the instruction before sending it to the arithmetic logic unit. Then everything forward it the display or the output. So your display can be a monitor, right? Then you can read the information book, right? So this is what's a typical diagram or a part of a digital computer. So like I said, I've talked about the central processing unit already. So the central processing is just the control and arithmetic logic unit are often considered as one unit called central processing unit, right? So the central processing unit is made up of two units, right? You have the ALU, which is the arithmetic logic unit, and then the control unit. I've explained the functions already for you. And then the CPU contains all the circuitry for fetching and interpreting instructions. So the control unit is the one that fetches what the information or the instruction from the memory and then decodes what it means before what sending it to what the arithmetic logic unit where mathematical manipulations are done. Then you see the results as at the what output. So the CPU contains all for fetching and interpreting instructions and for controlling and performing the various operations called for by the what instructions, right? This is what the CPU does. Then we look at our next topic will be types of what computers, right? So we can four main parts, right? Four main what classification. So you have the one that are classified based on physical size or size. We have one that are classified based on operating speed, and then you have the one that are classified based on memory capacity and then computational capacity, right? So there are three basic classification from what smallest to largest, right? When we say classification of you can see computers are classified by what physical size, operating size, memory capacity, and computational what capacity. But these are the types itself. We have the microcomputer, which are smaller, and then the mini. The microcontroller is smaller than the mini. So the mini is actually bigger than what? The micro. We have the microcomputer, the mini computer, and then we have the what? The mainframe, right? Mainframe. So we can look at them based on what the size, the operating speed, memory capacity, and all that. So the microcomputers have become more and more powerful. So they are powerful. So they have the higher operating speed than what the mini computers and then the mainframe, right? Then you have what? They have the smaller size as well. Then you have a higher memory capacity. And then you have what higher computational capacity. Then the mini has all of the what the classification has a better classification than what the mainframe. So the mainframe is the one with what the lowest what classification classification, right? So the distinction between microcomputers and the mini computer has become rather blurred, right? So it's just the operating is quite, I mean, smaller, right? But still, my computer performs much better than what the mini computers. So small computers, those that can fit in an office or a desktop or a lab. And then large computers are those that are what? That are too big for any of those places. Are we okay? So this will be our end of lecture one or chapter one. Thank you very much. If there is any question, let me know. Without any question, then we call it a day. So I'm listening. Any question?
No,
Any
sir.
question for me, please? So next week, without any question, next week we'll look at the logic gate, right? We look at
Yes, sir.
logic gate. Yes, we look at the various types of logic gate as well. Then we'll look at their symbol representation and then truth table and then the Boolean expressions. All right. So we'll look at
Okay.
that from next week going.
All
So
right.
like I said last week that whatever we do will be what uh, um, uh, how should I even put this thing? Will be a prerequisite to what we did last week. So what we did today will be a prerequisite to what we did to what we will do next week. So whatever we do here, you try to understand it very well before you get to what next week. Are we okay?
Okay,
So
sir.
next week is going to be very critical. So I want everybody to be present and then participate all the time. Then try to understand because without understanding the basics going forward is going to be very, very, very difficult. So I'll end here. Then we meet
Thank
next
you
week.
very much.
You're welcome. We meet next week.